Welcome to How the Heavens Go. I'm your host, Mark Lesmeister. Last time we looked at some geocentric models. These models, especially that of Claudius Ptolemy, dominated the Western conception of planetary motion for about 1500 years. There were still some astronomers who favored heliocentric models, especially in the Muslim world, but it wasn't until the 1500s when a Polish cleric came up with a workable sun-centered system that the idea began to take hold. We'll talk about that in a moment, but first let's look at what Bag 4 added to our model. Bag 4 was the final bag in the kit. It mainly involved assembling the Earth-Moon assembly that we attached to the arm of the model, and then it allows the whole thing to turn in unison. The Earth rotates, the Moon revolves around the Earth, and then the Earth-Moon system revolves around the Sun. This brings up an important point about intervals of time. Most people know that it takes about 365.25 days for the Earth to go around the Sun one time. So, to test the accuracy of our model, we should see if it takes 365.25 days for our model Earth to go around our model Sun. The question is, though, how do we count a day? Is a day the time it takes for the Earth to rotate one time? Remember, the day was defined long before we knew the Earth rotated. So a more earthbound definition of day might be the time for the Sun to be at its highest point in the sky, and then a day later when the Sun is once again at its highest point in the sky. But those two definitions of day are not the same. Let's see why this is so. Here's a diagram of the Earth rotating. Let's say one rotation occurs when the people on Earth are pointing in the same direction as they were previously relative to the fixed stars. This is called a sidereal day. The word sidereal comes from the Latin word for star. But at the same time the Earth is rotating, it is also revolving around the Sun. So it takes a little bit more than one rotation in order for the Sun to return to the same position in the sky. This is called a solar day. So now that we have all that figured out, let's go ahead and test the model very informally. I'm going to count sidereal days, which I will define as whenever I see Greenland passing in front of me, where I represent the fixed stars. So let's go ahead and count. 1, 2, 90. Let's go ahead and go 91. 91. So the model does appear to have gone a quarter of a rotation around, so 90 degrees or so. And that would indicate that our model is at least approximately correct. Okay, so back to our story. In our previous episode, we referred to the retrograde motion of planets. This refers to the way that planets, which normally appear to shift slightly to the east every night relative to the fixed stars, will start to shift to the west a little bit every night relative to the fixed stars. So, if we were to watch a planet over a period of nights in the southern sky, its motion might look something like this. In Ptolemy's model, retrograde motion was explained using two circles, a small one called an epicycle and a large one called a deferent. A planet would revolve along the epicycle, while the center of the epicycle revolved around the Earth along the deferent. However, in order to have agreement between the observed positions of the planet and the predicted positions from the model, Ptolemy had to offset the center of the Earth from the center of the deferent. The center of the deferent is called the eccentric. The need for eccentricity presented a problem for people who thought, for physical or philosophical reasons, that the Earth should be the center of motion in the planetary system. Another problem in Ptolemy's model was that the circular motion was not constant. The planet or the deferent moving in a circle would speed up or slow down. This contradicted the idea that circular motion in the heavens should be uniform. Ptolemy was able to preserve a semblance of uniform motion by identifying another point called the equant. The motion of the planet, when observed from the equant, would appear constant in angular speed. That is, it would cover the same angle in the same time. The equant was different for each planet. These problems were no doubt on the mind of the 16th century Polish cleric Nicholas Copernicus when he formulated his own theory of planetary motion. Copernicus first outlined his own heliocentric model in a manuscript known as the Commentariolus, the Little Commentary, copies of which he distributed to a few friends and colleagues. He delayed publishing his major work, De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, until 1543. The delay was likely more out of fear of being ridiculed for being wrong than fear of official disapproval. One of the major advances made by Copernicus was in determining the relative size of the planetary orbits. Ptolemy's system didn't include that. Ptolemy represented the motion of each planet with an epicycle and a deferent. He was able to calculate how big each planet's epicycle was compared to its deferent, but not how the size of each planet's deferent compared to the others. Copernicus reasoned that for the planets outside the Earth's orbit, the deferents were just showing the motion of the planets around the Sun. The epicycles, which bring the planet closer to us and farther away, are really just accounting for the orbit of the Earth, bringing us closer to then farther away from the planet. So the ratio of the size of the deferent to the size of the epicycle is the ratio of the planet's orbit to the Earth's orbit. The function of the epicycle and deferent are reversed for planets closer to the Sun, that is, Mercury and Venus. This allowed Copernicus to create for the first time an accurate representation of the size of the planetary orbits relative to the Earth's orbit. This diagram shows the orbits of Mercury, Venus, Earth, and Mars, treating them as circles. Another advantage of the model of Copernicus is that it provides us a simpler explanation for retrograde motion. It is just a consequence of the relative motion of two planets. Here is a diagram showing the orbits of Earth and Mars in a heliocentric system such as that of Copernicus. The relative sizes and durations of the orbits are approximately correct. Note the times that the Earth passes up Mars. This is similar to when two trains going in the same direction pass each other. From the point of view of the train that is passing the other, the slower train appears to be going backwards. When the Earth passes Mars, Mars appears to be moving backwards from the point of view of the Earth. Copernicus did not like the way Ptolemy's model did not have uniform circular motion, but only provided quasi-uniform circular motion when viewed from the equant. Copernicus wanted to do away with the equant, but that meant that in order for his model to match the observed motions of the planets, he had to add epicycles. Now, Copernicus's epicycles were smaller, much smaller than those of the Ptolemaic system, but they were there nonetheless. The popular conception of the Ptolemaic model was that it had multiple layers of epicycles, making it much more complicated than the Copernican system. However, both systems had about the same number of cycles. The Copernican system did offer a more natural explanation of retrograde motion, and it offered a way to calculate the relative sizes of the planetary orbits. Nevertheless, the model was slow in gaining acceptance. That acceptance would be aided by discoveries made decades later. We'll talk more about that in our next episode. Until then, look to the stars.